All right, hello and welcome back to my stream. Today we're working on the final part of the last blog entry of Philipp Oppermann's series, last to date blog entry of Philipp Oppermann's series on writing an operating system in Rust. I put a link to the series below in the info box. The last time we walked through what async await means and how it's implemented behind the scenes. And how the Rust, how the Rust compiler, I guess, implements it behind the scenes. And today, looks like what we're going to do is actually implement it for ourselves. So that's pretty exciting. I'm looking forward to getting that done. So let's dive right in. We are up to date, right? We haven't done any changes last time, so we're all set, ready to go. Implementation. Now that we understand how cooperative multitasking based on futures and async await works in Rust, it's time to add support for it to our kernel. Since the future trait is part of the core library and async await is a feature of the language itself, there's nothing special we need to do to use it in our no standard kernel. The only requirement is that we use at least nightly 2020-03-25 of Rust because async await was not no standard compatible before. I guess before that version. But we are more than recent enough nightly. So we can start using async await in our main RS. Let's try that. I guess it doesn't matter. We can just throw it here at the bottom. Async function, async number. Returns 42. We have another async function, example task. Let number is equal to async number await println async number is a number. Nice. The async number function is an async function, so the compiler transforms it into a state machine that implements future. Since the function only returns 42, the resulting future will directly return poll ready 42 on the first poll call. Like async number, the example task function is also an async function. It awaits the number returned by async number and then prints it using the println macro. To run the feature returned by example task, we need to call poll on it until it signals its completion by returning poll ready. To do this, we need to create a simple executor type or executor type. Before we start the executor implementation, we create a new task module with the task type. Okay, so this builds, right? It should build, yeah. And then we get warnings saying we're not using the function. That's fine. So if we go into source lib, and we can add this new pub. And then we're going to create source task and create mod.rs. Okay. Pin, pint. I keep doing pint. Why? Okay. Pub struct task future pin box din future output equal to nothing. Okay. The task struct is a new type wrapper around a pin heap allocated to dynamically dispatched future with the empty type as output. Let's go through it in detail. We got one line and we have 3 bullet points on it. Let's see, does this build? It does build. Oh, did I save the... Yeah, I did. Okay. Huh. Oh, I guess the warnings weren't related to that then. Let's take a look at what the warnings were, because I expected the warnings to stay based on the fact that example task is not called anywhere. If I comment this out, we get the warnings again. And if I put it back, oh, now we have two, okay. Oh, box. Oh, that's why. Alec box. Okay. That makes more sense. Now we have 5 warning. Okay. We just needed to reset our Rust analyzer thing. Okay, no problem. We require that the future associated with the task returns unit. This means that tasks don't return any result. They are just executed for its side effects, for their side effects. For example, the example task function we defined above has no return value, but it prints something to the screen as a side effect. The din keyword indicates that we store a trait object in the box. This means that the methods on the future are dynamically dispatched, which makes it possible to store different types of futures in the task type. This is important because each async function has its own type, and we want to be able to create multiple different tasks. As we learned in the section about pinning, the pin box type ensures that a value cannot be moved in memory by placing it on the heap and preventing the creation of mute references to it. This is important because futures generated by async await might be self-referential, i.e. contain pointers to itself, that would be invalidated when the future is moved. To allow creation of new task structs and futures, from futures, we create a new function. Okay. We could create a type that does this, right? We don't have to put it in each time, right? This should be self. I'm going to change this to self just because. Box, pin, future. Yeah. Pint. I see I did pint again. Okay. The function takes an arbitrary future with output type unit and pins it in memory through the box pin function. Then it wraps the box future in the task struct and returns it. The static lifetime is required here because the return task can live for an arbitrary time, so the future needs to be valid for that time too. We also add a poll method to allow the executor to poll the stored future. Okay, so we have core here, we have core pin, and we're going to add core task, context, and poll. So here's our poll function. This is private function. It returns a poll of type unit. Doesn't like that because I typoed it. And that doesn't exist. Okay, there we go. Since the poll method of the future trait expects to be called on pin mute t type, we use the pin as mute method to convert the self future field of type pin box t first. Then we call poll on the converted self future field and return the result. So you can get a mutable reference to the future even though it's pinned. Wasn't the whole point of not being able to mutate the pinned? Okay. Since the task poll method should only be called by the executor that we create in a moment, we keep the function private to the task module. Okay, simple executor. Since executors can be quite complex, we deliberately start with creating a very basic executor before we implement a more featureful executor later. For this, we first create a new task simple executor submodule. Okay, so we just put a pub mod simple executor here. Now this is going to blow up because this file doesn't exist, but it gives me the file name, so I can just do that. And use super task. Use alloc, collections, backdeck. Right, task queue, backdeck, task. Pub for new, simple executor. Oh, see, this should be self again, right? And we can just say self task queue backdeck new right? And then pub fun spawn, read self, task, self, task queue, push back. Okay. That seems pretty straightforward. And now it builds again. Okay. The struct contains a single task queue field of type DQ. I say vecdec because that's me. Which is basically a vector that allows to push and pop operations on both ends. I'd reword that slightly. Allows pushing and popping operations on both ends. The idea behind using this type is that we insert new tasks through the spawn method at the end and pop the next task for execution from the front. This way we get simple FIFO behavior. Dummy walker. In order to call the poll method, we need to create a context type which wraps a waker type. Oh, dummy waker, not dummy walker. To start simple, we will first create a dummy waker that does nothing. For this, we create a raw waker instance, which defines the implementation of the different waker methods, and then use waker from raw function to turn it into a waker. All right, we're back up here. Use core, task, waker, and raw waker. And we create a private function, dummy, raw waker, to do. Oh, okay. And then dummy waker, save, waker from raw, dummy raw waker. Epic Blog says, I saw that the Rust for Linux project uses async await for the kernel work queue. Amazing. It's really cool you're building a custom executor as part of this. Yeah, if I were smart enough to have done this on my own, I would be... Oh, here we go. There we go. Can't get that to compile. Okay, there we go. Yeah, no, I think this is really neat because the previous part... yesterday's stream, we actually talked through how async await works behind the scenes. And that helped me immensely in my mental model of how async await works. It was like the discussion that I was trying to Google for, and it was right here all along. So if I learned one useful thing about this, I do operating system programming for a living, so this is all kind of not new to me, but that part was definitely new to me. The from raw function is unsafe because undefined behavior can occur, or can occur if the programmer does not uphold the documented requirements of raw waker. Before we look at the implementation of the dummy raw waker function, we first try to understand how the raw waker type works. The raw waker type requires the programmer to explicitly define a virtual method table, vtable, that specifies the functions that should be called when the raw waker is cloned, woken, or dropped. The layout of this vtable is defined by the raw waker vtable type. Each function receives a star const unit argument that is basically a type erased self pointer to some struct, e.g. allocated on the heap. The reason for using a star const unit pointer instead of a proper reference is that the raw waker type should be non-generic but still support arbitrary types. Okay. The pointer value that is passed to the functions is the data pointer given to raw waker new. So this is interesting. It should be non-generic, probably because you don't want a separate implementation for each type, but it still needs to be able to support arbitrary types. So we create a star const unit pointer, which is actually the self ref, which I've lost in, I can't find now. Okay. Yeah, here it is, self-reference pointer to some struct. Okay. Typically, the raw waker is created for some heap allocated struct that is wrapped into the box or arc type. For such types, methods like box into raw can be used to convert the box t to a star const t pointer. This pointer then can be casted to an anonymous starconst unit pointer and passed to raw waker new. Since each vtable function receives the same starconst unit as an argument, the functions can safely cast the pointer back to a box t or a ref t to operate on it. As you can imagine, this process is highly dangerous and can easily lead to undefined behavior on mistakes. For this reason, manually creating a raw waker is not recommended unless necessary. A dummy raw waker. While manually creating a raw waker is not recommended, there is currently no other way to create a dummy waker that does nothing. Fortunately, the fact that we want to do nothing makes it relatively safe to implement the dummy raw waker function. Okay, so we also need to pull in the raw waker vtable. So our dummy raw waker is going to start here. No op and clone. Waker. This is kind of cheating, right? You're not really cloning it. You're just making a brand new copy of it, but that's fine. Vtable is equal to raw waker vtable new clone no op. Okay, we got to figure out what those no op functions really are meant to do here. 3 no ops. Raw waker new 0 as starconst vtable. So we're having a null pointer essentially here, right? Doesn't like that. Oh, because I put a semicolon there, right? There we go. First, we define 2 inner functions named noop and clone. The noop function takes a starconst unit pointer and does nothing. The clone function also takes a starconst unit pointer and returns a new raw waker by calling dummy raw waker again. We use these 2 functions to create a minimal raw waker vtable. The clone function is used for cloning operations, and the no-op function is used for all other operations. Since raw waker does nothing, it does not matter that we return a new raw waker from clone instead of cloning it. Yeah, it would be nice if they actually said what the other arguments are. Can we see that? Wake by ref, and drop. Those are the other 3 operations. And we're just no-opping them. So when wake is called, nothing happens. Wake by ref is called, nothing happens. And when drop is called, nothing happens. Okay. Neat. After creating the vtable, we use the raw waker new function to create the raw waker. The past starconst unit does not matter since none of the vtable functions uses it. For this reason, we simply pass a null pointer. Okay. Since we're not using it here, it doesn't matter what the value is. Fair enough. A run method. Now that we have a way to create a waker instance, we can use it to implement a run method on our executor. The most simple run method is to repeatedly poll all queue tasks in a loop until all are done. This is not very efficient since it does not utilize the notifications of the waker type, but it is an easy way to get things running. Okay. We need context and poll again. And then we're going to implement a run function here. Let some task equal to self task queue pop front. All right, so this is where we're doing the FIFO, right? So when we spawn it, we push back, and when we pop it, we pop front. Context from waker. Task done. And let me do that. Yep. The function uses a while let loop to handle all tasks in the task queue. For each task, it first creates a context type by wrapping a waker instance returned by our dummy waker function. Then it invokes the task poll method with this context. If the poll method returns poll ready, the task is finished and we can continue with the next task. If the task is still poll pending, we can add it to the back of the queue again, so it will be polled again in a subsequent loop operation. Trying it. Ooh. With our simple executor type, we can now try running the task returned by the example task function in our main RS. Okay, so let's go back to main. And now we need, in kernel main, we actually have to set up some stuff here. So here's kernel main, right? Initialization routines, including init heap. I guess we don't need this stuff anymore, right? This was just testing stuff. So we can blow all this away. It's in our repo. Was that right? Yeah, that was right. Okay, so then we just say let executor, simple executor new, spawn task, new example task. And we're actually calling example task. We're not passing a pointer to it. Run. Interesting. We're actually call this. Oh, because it's an async function, maybe it doesn't run right away. We have to await it or run it. Okay. Didn't like that. Oh, because I didn't import it. BlogOS. Task. Simple executor. Simple executor. There. Epic Blog says async functions return a future object. Okay, good to know. So no matter what, this is just returning an object that we then have to execute. Got it. Thank you. Glitch but small, thank you for the follow. Okay. Below is the example task function again, so you don't have to scroll up. Okay, fair enough. When we run it, we see that the expected async number 42 message is printed on the screen. We're still getting warnings. Oh, right, because I pulled those things out. Okay, so I can pull that whole alloc line out. We don't need that whole thing. Okay, so let's cargo run. There it is, async number 42, and it did not crash. Okay. Quit. Let's summarize the various steps that happen in this example, for this example. First, a new instance of our simple executor type is created with an empty task queue. Let's just pull this up here so we can have this on screen. Right here. Next, we call asynchronous example task function, which returns a future. We wrap this future in the task type, which moves it to the heap and pins it, and then add the task to the task queue of the executor through the spawn method. We then call the run method to start the execution of the single task in the queue. This involves popping the task from the front of the task queue, creating a raw waker for the task, converting it to a waker instance, and then creating a context instance from it, calling the poll method on the future of the task. Let's flip over there. All right, so we can see that here. Calling the poll method on the future of the task using the context we just created. Since the simple task does not wait for anything, it can directly run till its end on the first poll call. This is where async number 42 is printed. Since the example task directly returns poll ready, it is not added back to the task queue. Task is done. The run method returns after the task queue becomes empty. The execution of our kernel main function continues, and the it did not crash message is printed. We now have written our own executor in Rust for our own private operating system. That's worth celebrating. That's worth celebrating by checking it in. Okay, and now we're going to look at async keyboard input.